With all the stuff going on in the world today, I became obsessed with this vision of the Earth, seen from an incredible height. Maybe somehow if I could just gain enough perspective, the noise of life might fade away and some raw beauty could simply exist and tell its own story. But I wanted to try to create this vision with my own hands and not rely on images shared by others. I'm an engineer and a builder, and I don't sit still very well once I lock onto a vision. This is the story of the HAPP, the High Altitude Photography Platform, and the 2-year journey to make it real. So the basic idea sounds easy. Send a 360-degree camera up over 100,000 feet on a weather balloon and experience the edge of space in glorious virtual reality. And try to have some fun putting the project together as well. To do it right, you need a stabilized platform like a drone, but a drone won't work at that altitude because there's almost no air for the propellers to grab onto. It's 99% of the way to the vacuum of space and about minus 50 degrees Fahrenheit to boot. So now you have to start thinking like a spacecraft designer. I decided to use a reaction control system, or RCS, little jets that fire rapidly to stabilize the craft, because I thought it would be the simplest way to do it. Simple is good because I wanted to keep this a do-it-yourself project using tools, parts, and methods that anyone can replicate in their garage. Of course, simple is a relative term. I honestly thought I'd be done in 2 or 3 months. And did I mention this project was supposed to be for fun? Okay, so I was off by more than a factor of 10. 22 months, not 2. What took so long? Well, brushing up on controls theory, building a control simulation, implementing the control software on an Arduino after learning how to code Arduinos, designing compact and lightweight pneumatics for the jet stabilization system, figuring out the jet nozzle theory, nozzle design, and nozzle 3D printing, parachute system design, structural design, building a new PC to run the software for various simulations, which by now were getting pretty complex, structural component manufacturing and assembly, camera selection, balloon tether design, optimization, and manufacturing, parachute tether design, optimization, and manufacturing, developing a process to manufacture custom carbon fiber aeroshells in my basement, starting with a full-scale model called a plug, then using the plug to make an orange fiberglass mold, then using the mold to lay up the carbon fiber and enclose it in an airtight bag, then finally injecting resin using vacuum infusion, and producing 2 copies of the aeroshell, just in case. Then finding a friend to help build the satellite-based communication system and software, finding more friends to build a cool app for tracking the HAPP on a mobile phone, figuring out the various power buses and electronics architecture, building the flight computers, packaging everything into the HAPP with good balance and aerodynamic stability, finding a sufficiently large balloon and a source for lots of helium, learning how to rig a large balloon with the fairly heavy payload and pyrotechnic cut-down devices, working with the Federal Aviation Administration to figure out the flight logistics, and testing. Simple, right? In the end, I wound up with 5 key systems: a carbon fiber and aluminum core, the RCS for stabilization, the ELS with explosive mortars for parachutes, all the electronics to make it work, And of course, the carbon fiber and Kevlar aeroshell, all in a modular and serviceable design. But enough of the pre-flight briefing. It's time to head out to the launch pad and strap into the HAPP for its first shakedown mission. We're launching from cornfields in Ohio, not Kennedy Space Center in Florida, but it should still be a great ride. Let's go join the ground crew as they prepare for launch.
We never know. Ooh. You have to keep your things stable. Ooh, there is the HAPP shell.
HAPP-M1, this is Mission Control. Welcome on board. Take a look at your heads-up display. It's showing actual data from the flight computers. You can see in mission status that we've been cleared for ascent by Cleveland and Chicago Air Traffic Control Centers, and the onboard computers have finished their pre-flight checks. In navigation, you can see that we're launching from about 700 feet above mean sea level here in northeastern Ohio. Keep an eye on the dynamics to check our spin rate and vertical velocity. And finally, in environmental, you can see that we're currently experiencing about 1 atmosphere of air pressure. That's going to go way down today as we climb above most of the atmosphere. Okay, let's turn it over to the ground crew for final preparations. It's time to kick the tires and light the fires.
All right, start at 5.
5,
5, 4, 3, 2, 1. HAPP-M1 is away. Godspeed, HAPP-M1.
Oh my god. I got the camera. Woo! Ascent!
HAPP-1, you cleared the launch zone and flight computers have detected initial ascent. Godspeed. You'll notice the HAPP is slowly spinning. The jets can stop the spin, but it takes a lot of gas. So the flight program will pulse the jets just enough to limit the spin. There they go. As you reach certain altitude thresholds, the jets will completely null out the spin for a few moments to give you a nice view. There's threshold 2. Approaching altitude threshold 3. From there you're entering the jet stream and the flight program will temporarily disable stabilization. No use wasting all that gas fighting extreme winds. Threshold 4. You're now over the jet stream and stabilization has been re-enabled. It should be a fairly smooth flight from here on up. You've also exceeded the altitude of all commercial jet flights. As you approach threshold 5, look at the balloon icon in the mission status panel. It's already more than doubled in size at this altitude. The ground crew intentionally overfilled the balloon for this maiden flight to ensure a quick climb and a clean balloon burst, so we probably won't achieve 100,000 feet before it pops. Let's see what happens. Threshold 5, you're now twice as high as a commercial jet. That sky is looking pretty black as you get closer to space. HAPP-1, the balloon is now critical. Prepare for descent. HAPP-1, we have a problem. The small blue cut-down pyros fired and severed the balloon tether. The balloon is supposed to fall away, but the tether got tangled with a small red drogue parachute, and about 3 kilograms of latex are coming down with us. You're falling at about 10,000 feet per minute, but the HAPP is not stable with all of that balloon material fluttering in the airstream. Better hang on. I'm freezing the video feed because you entered into a hard spin, but the heads-up display is still live. Look at your spin rate in the dynamics panel. You're descending through 10,000 feet and the spin has settled down in the thicker atmosphere. You've also slowed your vertical velocity down to about 3,500 feet per minute. Stand by for chute deployment. shoots away. But there's another problem. As the chutes inflate, one of them eats the balloon material, and that chute becomes dead weight. There's chute 1, chute 2, chute 3, and chute 3 eats the balloon. The excessive spin also creates a messy tangle with the chute lines. You can see chute 3 dangling below the HAPP. The extra 6 pounds or so of material are making us fall faster than expected, and we're missing 1 parachute. The HAPP was designed to come down safely on 2, so hopefully you won't make an impact crater. The landing zone elevation is 708 feet mean sea level. On approach. Touchdown. HAPP-1, good to see you're still in one piece. Stand by for the recovery team. They've got you on their tracking app and are inbound to your position. We've got a few issues to improve for the next flight, but congratulations on earning your wings. HAPP-1, this is Mission Control signing off.